Already. Let's double check that we're working today. Let's see here. How are we going to be working? Looks good. Okay, things seem to be working today, so that's always nice to see. We're going to continue talking about acids and bases today. So kind of yesterday we talked about conjugates. We talked about defining acids and bases. We looked at some of the reverse reactions and sort of thing. We've talked about strong acids and strong bases. And we've seen that certain compounds that were amphiprotic or amphoteric can act as either acids or bases in the right conditions. Hold on, I'm gonna sneeze. Excuse me, damn allergies. All right. So today then, let's go ahead and talk about quantifying acids. So we know that according to our Arrhenius definition, at least, acids produce H plus in solution, right? In water specifically. And we're going to see that this value is actually going to go anywhere from 10 to the 1 to 10 to the minus 15 or so. So we have a huge range of potential concentrations of H plus that we're going to deal with. And so it's kind of less useful to use these exponent terms. And so what we do is we often will take the logarithm of these. And so what we do is, so H plus can go from these ranges in molar concentration, that is. We're going to see that we can take these same numbers, and by using logarithms, we can make them a little bit more easy to understand, a little bit easier to use. So what we do is, remember that the log of 10 to the 1 is just 1. Log of 10 to the minus 3 is minus 3. Remember, log just takes your exponent off your base 10, and there you go. You may have some other stuff afterwards. For example, log of 2 times 10 to the negative 3 is going to give us, I don't know, where's my calculator? Aha! Alright, log 2 times 10 to the negative 3 will give us negative 2.7, for example. So we have our 2 there that's a little bit bigger. That's why we're going to have our number be a little bit bigger than the negative 3 there. So when you're doing logarithms, you're going to want to definitely play with your calculator. Each calculator does it differently. I'm using a TI-84. In this, you can potentially see what I've done. I just type in log 2e negative 3, and poof, there's my answer. However, some calculators will have you punch in the number first and then press log afterwards. And so it just depends on what your calculator wants to do. So you'll definitely want to take some time practicing with your calculator. Believe it or not, I say this every semester and still people don't listen to me. If you do not practice with your calculator, if it's not in your muscle memory, when it comes to exam time, you're going to be wasting time looking on your calculator, like, okay, where the hell's the log button? Oh, why is it giving me syntax error? Oh, why is it blah, 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 not working? Why is it giving me a positive number when it should be negative? You know, it's super important that you understand how your calculator works. So for what most students use, I have put a video in the textbook showing how to use logarithms on there, but you will want to make sure that you can generate yourself all of the numbers that we're going to get through in lecture. So make sure that when you input all these values that you get the same answers out. And try around, look on YouTube with your particular calculator model and see what you're doing. Or if you're just using an online calculator, play around with that too. So You know, whatever you're using, make sure you are super comfortable with it so you're not wasting time on your final trying to figure out how to do logs. Anyways, soapbox speech over. Just so we know, since we are absolutely hating our sig figs, if we look at this original number, this is just one sig fig, right? Which comes from the 2. Remember that these do not give significant figures. They're just going to tell us kind of where we are. So this is just telling us this is a really small number. But it does not give us any significant figures. Only the significant figures come from that base number. And so, as a result, with logarithms, since this didn't have any sig figs, that tells us that this number doesn't have any sig figs either. And same thing here. This number had no sig figs, therefore that number has no sig figs. And so, the number that's before the decimal in a calculated logarithm do not contribute to sig figs. So if we do that again, this log of 2 times 10 to the negative 3 was negative 2.7. This number has 1 sig fig. This number also has 1 sig fig, and that's the 7. The 2 there is just to tell us how big or how small the number is. It doesn't tell us anything about the number itself. So that's just your exponent term. And so since that did not have significance to begin with, that does not carry significance in your final answer. So only numbers after the decimal will matter. All right, so if I gave you log of 2.00 times 10 to the negative third, same number, we have it here in our calculator still. If we round it, it's 2.699. This number has 3 sig figs. Only numbers after the decimal count for logarithms once you've calculated them. This number had 3 sig figs going in. That number has 3 sig figs coming out. Alright, so numbers before the decimal don't matter, no matter how many there are. So if we do it, let's do another one. If we do log of, I don't know, 8.21 times 10 to the negative 12, calculator. For me, I put the log button, 8.21 e negative 12. I get negative 11.08565684. This number had 3 sig figs originally, so we need to keep 3 sig figs in our answer. Remember that the 11 does not count because that is for our exponent. So if we round this, we get 11.086. Sorry, it's negative. So the 0, the 8, and the 6 are all significant there. The 11 does not count for sig figs. Alright, so something to keep in mind. Sig figs for logarithms do not include numbers before the decimal. Alright, so we can just pretend those aren't there. Alright. Alright, so logarithms are already a pain in the ass, but that's okay. The whole point of doing this is that we're going to see it's going to make things a little bit easier for us. We're going to see that we use something called pH a lot stands for power of hydrogen. Like 10 to the power of, that sort of power, not like, what is power? Joules per second, so energy over time. That would be power, right? So power of hydrogen is exponent power. And what we do for it is we take the negative log of the H plus concentration, whatever we're looking at. These brackets mean concentration in units of molar. And so we're going to see that, for example, if we take a sample of 0.125 molar HCl, we know HCl is a strong acid, so HCl will break up entirely into its ions as a strong electrolyte, and therefore we can figure out what the pH of this solution is going to be. Well, it will just be negative log of 0.125. That's this value here that we're plugging in. We use the negative log because often we're going to have negative exponents, so we just like everything to be positive, so that's why we do that. So let's do this. So negative log 0.125, and we get 0.903. And that number has 3 sig figs, so we're good. No units for pH. Once you do a logarithm, your units go out the window, so there are no units here. All right, how about if we had that number molar nitric acid? Well, thankfully for us, again, nitric acid is a strong acid. Being a strong acid, it completely dissociates, which means out of this, we get that same amount of H plus. So for our strong acids, remember, it's going to be equivalent to your concentration. So your acid concentration and your H plus concentration are the same if it's a strong acid, because strong acids are strong electrolytes, they break up completely. All right, so if we do this, the pH of this solution, we can do that too, negative log 2.62 E negative 4. Out of that, we get 3.582. All right, let's just do one more. What about if I have H plus equals 4.91 times 10 to the negative 10 molar? What's the pH of this one going to be? All right, here we go. Negative log 4.91 E negative 10. Into this we should get 9.309, it looks like. All right, so I think that's a good enough. Oh, it's pretty interesting that we have all the same numbers here. It's a kind of broad view here. We can see that we had kind of our highest acid concentration of these three that we did. We had 10 to the negative 4, 10 to the negative 10, and then 10 to the minus 1 as our concentrations. And we see we in fact have our lowest pH for that same value, which tells us that as H plus increases, pH decreases. So they are opposite scales to each other. So pH typically runs from about 0 to 14, though it can certainly exceed either side. You can have negative pHs, you can have pHs above 14, but most pHs lie within this range. And so, as we see here, the most acid means your lowest pH. So you're going to have the most acidic solutions down here. And therefore, on the opposite side, we're going to have the most basic solutions. All right, so we're going to see that most things that follow the scale, we can kind of judge how basic or acidic they are looking at their pHs. We're going to see right in the middle here is pH 7, which we consider neutral. We'll talk about that in just a second, about why it's 7 there. Not only is it, halfway in between, but there's another reason for that. All right. Any questions so far? So low pH means is very acidic, high pH means more basic. Or you might see the word alkaline. Alkaline means basic, same thing. So an alkaline battery is a basic battery, one that has a basic solution inside, versus your acid battery, which is in your car. You have an acid battery in there. Alrighty, so we're going to see that if we just kind of look at these, there's a lot of kind of common things that we might see around here. Around pH, I don't know, 5 to 6 or so. Somewhere in there you have rainwater. You have milk around here. Go down to like 4-ish area, that's where you have coffee, sodas, that sort of thing. Go down to 3 or so, that's where you've got your lemon juice. You've got your stomach down here around 1 or 0. So we're going to say that a lot of the like food products that we think about, a lot of them are going to be acidic, which I guess is bad news for our dentists, or good news because then they'll make money, but we'll lose our teeth. So we're going to, if you take 113, you'll learn why acids will destroy your teeth, but that's neither here nor there. pH 7 would be distilled water, right around pH 7 or so. Right at 7.4 is our blood, right here at 7.4. Very, very specific pH values there. Around pH 9 is where your bones are. Your bones are a little bit more basic than the rest of your body. 10 and 11, that area, you're getting into like Windex and other kind of cleaning agents. Ammonia, they're all up here. They're all up there in the kind of higher pH range. And then, you get to like lye, which is sodium hydroxide up there. Bleach is also going to be fairly basic. So just some like rough examples of things that we deal with every day, that just so you can kind of see that there's a whole range of solutions that we're going to come into. And so we're going to consider that solutions that lie between 0 and 7 are just going to be acidic solutions in general. And these ones will be basic solutions. So pH is above 7. whereas these are pH below 7. 7 is our midpoint. That's where we're declaring it to be neutral, and we'll see why that is in just a little bit. Okay. What's interesting, pH is so important. So your blood has a normal pH of 7.46. That's pretty standard. If you go up to about if you change your blood pH, which you can't, by the way, but if you were in a disease state, this would be alkalosis here. This would be acidosis. Prolonged, time spent in these kind of conditions makes you very, very sick. If you go kind of beyond that, even to maybe 7.6 or so, you die. And if you go really below that to say maybe 7 or so, you die. So your blood is extremely well kept at a very specific pH range. If we see the difference here, this is the difference of 0.1 pH units or so. pH again doesn't really have a unit, but that means, so 1 pH unit, by the way, is a factor of 10, right? So going from pH 3 to pH 2, you become 10 times more acidic, since that's how logarithms work, the powers of 10, instead of just 1 pH unit that's really 10 times more acidic. 0.1 pH unit, let's see what that's going to be, is about 0.8 times as acidic or basic as your blood. So it's a relatively large difference, but that's enough to kill you. So you can get into acidosis by alkalosis by hyperventilating. It means you breathe too much, you spit out too much carbon dioxide. Carbon dioxide is an acid, by the way. So as you get rid of too much carbon dioxide by hyperventilating, you end up making your blood more acidic, more alkaline, and then you start feeling dizzy, you pass out. That's why if you are going to hyperventilate, you've seen it in the movies or whatever, people will breathe into a paper bag, because that'll prevent the CO2 from going out so they can get it back and not hyperventilate. So our bodies are very, very, very good at maintaining this pH, and we use a whole bunch of different systems to do so, but one of the main ones is carbon dioxide and bicarbonate. We keep these things very, very tight. The opposite side, if you stop breathing, so if you slow down your breathing too much, you end up going into acidosis. Or if you spend a long time in ketoacidosis, hint, that's one of the fad diets now, you'll make yourself sick too. However, our bodies do have ways of compensating a bit for this. To kind of fix these things, your lungs and your kidneys work very hard in tandem to keep your blood pH very specifically at 7.46. So in order to do that. So if you are hypoventilating just over time, your body's kidneys will adjust for that. So the lungs and kidneys kind of work in opposite ways, so they'll be able to help each other out. So where was I going with this? Oh yes, it may not be the best idea for people to specifically trigger their body to going into ketosis, because ketones are acidic. You're putting more acid in than your blood can deal with. It's not a good idea. So please use moderation if you are planning on such a diet. Another thing that is people buy into because they think it's cool is alkaline water. They think drinking water at pH 9 or whatever, or 10 or whatever it is, will cure their cancer or whatever. Consider that alkaline water, which is very slightly alkaline, goes straight into your stomach, which has a pH of 1, strongly acidic, can be completely negated right then and there. But even so, to try and force your body to go more alkaline would not be a good thing. So if you start injecting yourself with alkaline water, please do not. That's a very bad idea. You will end up with problems. So it's another kind of, unfortunately, a lot of humans have not taken chemistry, so they don't understand these things, so they can be bought out by some of the gimmicks people like to throw around. But waste of money. If you like the taste or whatever, great, that's fine. But if you're trying to do it for health reasons, there's no point. Once you get into doing calculations with acids and bases, you will see very, very quickly that your stomach will very, very rapidly neutralize any alkaline water that you're drinking. And so, sad times. Anyways, that's enough biology. Let's get back into chemistry. So, anyways, you're going to see also that we have things called buffers here that also help to maintain. We'll talk about buffers at the end of the chapter, though. So, right now, I'm just kind of showing you the value of pH. We're going to see that many biological functions do depend strongly on pH. So enzymes need to have a certain amount of protons in solution to be able to function properly. So the ones in your stomach need a lot of protons in order to get into the right shape so they can start breaking down proteins, other proteins that is. And ones in your other areas of your body need less acidic pH to function properly. And so we're going to see that enzyme function and basically your life is very strictly dependent on pH. So, but that's biology. I'll let you deal with that there. So, yeah, good stuff. All right. Anyways, so that's some pH stuff for us. Let's talk about why is 7 the neutral one? Well, we see that water has a pH of 7, pure water. So nothing else in it, no dissolved gases, no dissolved solids, nothing. Just pure water has a pH of 7. And the reason for that indicates, by the way, that we have an H plus concentration of 10 to the minus 7 in pure water, which is odd because pure water should just be water, but it turns out that water can react with itself to form, remember as we call it, H plus and OH minus. And we're going to see that this is a process called the autoionization of water. It doesn't happen very often. 10 to the minus 7 is 1 out of 10 million. Excuse me. So if you have 10 million water molecules, one of them will have split up into ions. And so not a huge amount, but it's not zero either. And so we're going to see that because of this, if we see that this is 10 to the minus 7, And since the water is splitting up evenly into H plus and OH minus, that tells us that the OH minus concentration is also 10 to the minus 7. They split up equally, right? If you take your water molecule, take off one proton, you're left with one hydroxide. And so as a result, you have a 1-to-1 ratio there. And as a result, we have kind of established this as a constant, which we call Kw. K, you'll find out later in 113, is your equilibrium constant, but that's not something we have to worry about now. Which is the product of your hydrogen ion and hydroxide ion concentration. And so for pure water, this is going to be 10 to the minus 14. All right, and so this is a number that's going to be extremely valuable for us because it's going to tell us if we know our hydrogen ion concentration, we can figure out what the hydroxide ion concentration is going to be for that solution. And so we'll have some examples of that. A couple things to notice here. Technically, the units are molar squared, but most people don't include them, so we don't care. This value is also only true at 25 degrees Celsius. It does change a little bit with temperature, but for our class, it's always 10 to the minus 14, and we're going to treat it as an exact number. So we're not going to worry about sig figs with Kw. All right, though in reality it is an experimental value, and we would have to see what temperature it is and all that. But oops, for us, always 10 to the minus 14. That's it, and it's going to have no significance for us. All right, so if we take a look at some of those things we did before, we can now calculate in solution. For example, we had this 0.125 molar HCl. Remember that gave us 0.125 molar H plus. We could figure out what the OH minus is going to be by understanding that H plus times OH minus in a solution will always equal Kw. And so it's simply a matter of plugging this in. So therefore, OH minus concentration will be equal to 10 to the minus 14 divided by H plus, or for us, it's 10 to the minus 14 over 0.125. Calculator. So one thing to note about 10 to the minus 14, the way that I would enter this on my calculator is like this. I put 1 as my base number, EE, which is represented by that capital E there, minus 14, divided by 0.125. And so with this we get 8 times 10 to the negative 14. With that, by the way, if you want to use the 10 to the power of function on your calculator, you can do that for this. You can just go ahead and put in 10 to the minus 14, but you might have to just be very careful. See, if I just press enter on that, it spits out what I had before, the 1e negative 14. That's kind of calculator language, the most common way to do it. So this kind of EE button, I know this is a TI-84, but let's see. Come on, focus, silly camera. Focus on this EE. You can do it. Don't focus on my head. Oh, it's so hard to like. Okay, well, whatever. You can't see it. But there is an EE button. That's what I'm typing out there. 1EE negative 14. That's what I would put on the top. Okay, anyways, we have the wrong sig figs for this number. We need to round this appropriately to 3 sig figs, by the way. And that would be our concentration of hydroxide ions. So with that, we can see now we've seen that the concentration of hydroxide is really, really low in this superacidic condition, superacidic solution rather. If we take a look at that other one we had, the next one was 2.62 times 10 to the negative 4. We had the nitric acid solution. We're going to see that OH minus would be 10 to the minus 14 over that number. Bust out your calculator. Alright, so 1E negative 14 divided by 2.62E negative 4. We should get out 3.817 times 10 to the negative 11 molar. And if we do it for our last one as well, let me just zip up here real quick. We had 4.91 times 10 to the negative 10. Okay. So OH minus for this solution, so 10 to the minus 14 divided by 4.91 times 10 to the minus 10. I will write that. This time we get 2.037 times 10 to the negative 5 molar. So we see here these numbers are getting bigger while these numbers are getting smaller. Oh my gosh. And I mean, we can already tell, if we have these as constants, or rather if we have them multiplied equal to a constant, we see as hydrogen goes up, OH minus goes down, and vice versa. So these are directly or inversely proportional to each other. And so, if we look back to our pH scale, the most acidic ones had high H plus concentration. We're going to see that the alkaline ones will in fact have high OH minus concentration, which we would expect if we're defining bases as things that produce OH minus. The more basic we have it, the more OH minus we have. So we're going to see that again, these are going to be the opposite of each other. Scroll down here. All right. If we want, sometimes we also talk about POH, which is the same calculation for hydrogen, but instead we use hydroxide. We can do this for all of these as well. So let's see what the pH of these, or POH of these would be. So I'm just going to call this solution 1, solution 2, solution 3. All right, so for solution 1, if we were to find its POH, 8 times 10 to the negative 14, calculator. Negative log 8e negative 14. We get 13 point let's see, wow, do we really have that many sig figs for this? Oh, I'm sorry, this should only have been 2 zeros. Okay, so we have 0, 9, 7 there. If we just take a look at solutions 2 and 3, actually let me leave a little bit of space. I'm just taking the numbers that we just calculated, 3.817. See, shame on me, I've given these 4 significance, they all should have had 3. To the negative, what was it, 11. All right, let's do it. Negative log 3.817 times 10 to the negative 11. All right, our POH is 10.418. This one too, and our last solution 2.037 times the negative 5. 2.037. Sorry to have to keep scrolling up and down, but we must get these values. Okay, we're going to see something cool with these. 0.037 times 10 to the negative 5. Oopsies. Oh, I put 0.5. Negative 5. Okay, there we go. So we have 4.691. All right, tons of calculations. All right, any questions on these? Plug and chug, I get it. Let's take a look at what the pHs were for all of these. While we're here, might as well. If we scroll all the way up, the pHs were 0.903. Sorry to have to, I just need to write these down real quick, then we'll go back. 3.582. And then 9.309. Okay. Do we notice anything about these? Maybe. Perhaps what we might notice is that if we add them up, they get to be 14, which is interesting. Okay, let's verify. 0.903 plus 13.097. Aha, 14. If you check the rest of the numbers, you'll see that those two, or solutions 2 and 3, will also add up to 14 if you do that. Exciting stuff. We can figure this out through other means, though. If you remember that it's H plus times OH minus 10 to the minus 14. We have to remember that log x, y equals log x plus log y. That's one of our rules of logarithms. So we take the log of both sides of this, we get log h plus log oh minus equals negative 14. And if we multiply everything by negative 1, we get minus log h plus minus log oh minus equals 14. And remember that negative log is the same as p. So we get ph plus poh equals 14. So we can get this just mathematically as well. You don't need to understand the derivation here. And so that's what I've done mathematically there. But we get the same thing here. So we can very easily compare the pH and the POH of solutions together by having to understand that because they're inversely related, we can add them up and get a constant. And if we scroll all the way back up here, we saw that this was a low pH, but that also means, therefore, a high POH. And it'll be the opposite on the other side, and I have no room. So low POH would mean a more basic solution, and that would be a high pH. No room whatsoever, shame on me. So, we've so far got quite a few equations here that we can work with. We see that pH equals negative log of H plus. If we wanted to do the opposite of these, if we were given a pH and asked to find an acid concentration, we would just do the opposite. We're going to see the opposite of a log is 10 to the x. So we're going to see that H plus, we could also say, is 10 to the minus pH. It's the opposite function of log by raising it now to the power of 10. And for OH concentration, that's 10 to the minus POH. And you can get your OH concentration out. Let's see if I'm lying to you, which I might be because of slight rounding errors, but let's do it. So if you notice, I guess I can't show you, but maybe if you like zoom in or something, if you find your log button, oftentimes the shift or second log button will be 10 to the x, because it's the opposite of logarithms. So I'm going to press 10 to the x, 10 to the x, and I'm going to put my negative POH in. So if my POH was 4.691, I'm going to put negative 4.691. What I get out, if we can see the value there, is 2.037 times 10 to the negative 5. Notice that's in fact what we had put in beforehand. So we do get the value out again if we do the opposite function. So lucky us, we can go back and forth. We also saw that these multiplied together is 10 to the minus 14, technically at 25 degrees Celsius. Not going to worry about that. And so we now have 6 formulas here that we can use to get all sorts of things. So if we are given we can go from H plus to pH by using the negative log. We could go to OH minus by using kW, which was 10 to the minus 14. We can also go to POH by doing the negative log of OH minus, or we can use that formula there. So now, given one of these four things, you can calculate the rest of them. So I can give you pH, you can calculate H plus POH and OH minus off of that. Or I can give you POH and you calculate the other three. And so we have a lot of, I don't want to say fun, but fun things I can do with it. So let's do it. All right, I'm giving you a POH. Let's see if we can't get everything else. We can do this. So if POH is 8.92, right away we can find the pH, or we could find the OH minus concentration. Those two we can calculate directly from POH. Those are linked together. So just like here, we're now just going the opposite direction. If we do this, we do the opposite equation here. So we can calculate this one first, why not? So OH minus should equal 10 to the negative POH, which will be 10 to the negative 8.92. Calculation time. 10 to the negative 8.92 gives us 1.2. How many sig figs? Looks like we have 2 sig figs, so that's enough. And we're given our concentration there. Alright, if we wanted to find pH, well, that would just be 14 minus POH, right? If added together they're 14, I can just move the POH to the other side. So 14 minus 8.92. Hopefully I don't need to make calculator. 5.08. And our last one is H plus that we need to find. We have two options. We could do it this way, Kw over OH minus, or we could do 10 to the minus pH. I think it's a little bit easier to do the second one. Just you have to press fewer buttons. But you should see that both of them will give the same answer. So let's just do it both ways. So let's try it first with Kw. We've calculated our OH concentration. So let's see. So 10 to the 14 divided by 1.2 e negative 9 gives us 8.3 times 10 to the negative 6th. And let's just try it with the other way. Our pH we calculated 5.08. So 10 to the minus 5.08 gives us 8.3 times 10 to the negative 6. These should have been the same, right? So we are happy there. There will be a slight difference because of rounding, perhaps, but in this case, they were both the same to the same significant digit, so we were okay there. So, fun stuff. Yes, you can calculate all manner of good stuff. These units by the Baron molarity. So we can do all sorts of fun math here. Let me pop over to Canvas real quick so we can take a look at some of the practice that I've got for you. Alright, here we go. What are we doing? Practice, practice. Aha. So, I have two practice things for you here. This is your home page on Canvas with my 8,000 tabs open. One of these is on pH practice. Wait, what is this? Okay, hold on. This link is not working anymore. I'll fix the link. Let's see here. Yeah, they've changed their website. Okay, so I have to fix that. But if we look at the acid-base practice, I checked that one yesterday. That one's still working, though apparently it wants us to open it in a new tab. For us, we would only want to look at the first 4 pages of this, because after that they start going into more complex stuff. So there are some good multiple choice questions here that we could work with. Skip number 12. That's not something that we cover in this class, but there are some good things. You could figure out conjugate base pairs. You could do some pH calculations here. Or there's OH and POH. I mean, all sorts of fun stuff here. So I would stick to the first 4 pages or so and skip number 12. And I believe the answers are at the back. So you can scroll all the way down to see the answers to make sure that you're getting things correct. So these would be similar questions that you can expect on your exam. All right, so these would be of approximately the same difficulty. So you want to make sure that you are very comfortable with all of these sorts of things. Okay? Yeah, so there we have it. I'll go ahead and double check the pH practice link because that one clearly is not working, but it used to be an engine that you could plug in your H plus value or whatever, and it would spit out the other 4 or other 3. So you could just make up a pH and get all and calculate them all yourself, and then double check your answers with it. So I'll fix that. So okay, awesome. It's Wednesday. That means it's the weekend for us, at least for this class. So again, I think you just have a lab sim left. That's the only thing left to do. Again, I'm not giving you homework on this, so it's up to you. Next week we'll continue on. We have a few more things to do with this chapter. We may finish Monday, we may finish Tuesday, just depending on how quick we go. And so we'll then have some time for review. So as always, I would expect it'd be good to post some questions if you have questions about this, like practice worksheet or whatever. That would be a good place to draw them from, or say, hey, on exam 4 I got this question wrong and I really have no idea why. That could be something we can do as well, because that'll definitely help you review for your final exam. So yeah, cool, awesome. Cool. I guess I'll see you on Monday then. So have a great weekend. I think it's going to be getting pretty warm, so stay cool over the weekend. So, but enjoy. See you on Monday.